We're going to work some additional examples on functions defined as integrals to try to cover other little nuances and common mistakes that students make. So we'll just dive into some more examples and kind of walk through these types of problems. So here's one that says the graph of a function f consists of a semicircle and two line segments as shown below. Let g be the function defined as g of x equals the integral from 0 to x of f of t dt. So once again, we know that f of x is the graph that they've given us here, and that g is the area accumulating in the plane starting at 0 and stopping wherever they tell us between f and its horizontal axis. So part A says find g of 3. Well, g of 3, and you need to show this step. Once again, you've got to show the AP reader that you understand the accumulation function means to accumulate the area starting at 0 and stopping at 3. The biggest kind of curveball here is that students are going to have the tendency to want to start accumulating at -2 because it's part of the graph, but this clearly says to start accumulating at 0 and stop accumulating at 3. So we need this area, which is going to be positive area, and we need this area, which is going to be negative area. So since they told us it is a semicircle, we don't have to, be curious as to whether it is elliptical or whatever. We can clearly see this circle has a radius of 2 because that's 2 along the x-axis, 2 along the y-axis. So we want a quarter of that circle. So we're going to show them that it's a quarter of the circle, and the area of a circle is pi r squared, and we said that we can see that r is 2. So there's the positive area, and then we're going to subtract from that the area of this little triangle. So in this context, areas of geometric figures, you need to make sure and have those ready in your brain to pull up. And the area of a triangle is 1/2 the base times the height. The base of this triangle is a +1, and the height of this triangle is a -1, but I've already dealt with the negative right here. We could put plus 1/2, a base of 1, and a height of -1, and that would deal with the negative as well. And it really doesn't matter. You just need to make sure that you are subtracting this area. So this cleans up, and I wouldn't have to clean it up if it's a free response question, but this 4 down here and this 4 up here cancel. So we wind up with pi minus 1/2. So there is actually g of 3. So again, make sure you start accumulating where they tell you to start accumulating. Find all values of x on the entire open interval from -2 to 5, at which g has a relative maximum. Now look what they did here for us. They threw the endpoints out because on relative maxes and mins, the endpoints don't count. The endpoints are only critical points for us if they want absolutes or globals. So basically what we're looking for is we're going to have to tell them we understand that g prime is the derivative with respect to x from 0 up to x of f of t dt, and that we understand from fundamental theorem part 2 that that is the graph of f. So when we start using f as g prime to talk about where our relative maximums occur, then we've got the basis here to make that argument using the outputs of f. And again, g will have a relative, it's an R, my R's and V's look a lot alike, a relative max when g prime of x, which we already said is f of x, changes from positive to negative. So I need to look from -2 to 5 at all the instances where the outputs of this function go from positive outputs to negative outputs. This is a negative output to a positive output. So the one and only relative max on the interval from -2 to 5 that g has is at x equal 2. This occurs at x equal 2. All right, so C, write an equation for the line tangent to the graph of g at x equal 3. Remember me saying, and I think I have, proven this so far, that in any context they can put you in, they're going to ask for the equation of that tangent line. And this is in the context of a function defined as an integral. So if g of x is the integral from 0 to x of f of t dt, then I need the point 3 something. I need to find out what the y coordinate is when x is 3. And I also need g prime of 3 because that's going to be my slope. And then I'm going to plug that into y minus y1 equals the slope times x minus x1, right? Point slope equation. So I need the point and I need the slope. I have the x coordinate already. And if you'll think of it, this is g of 3. And we already found that in part A. We found that to be pi minus 1/2. So we don't have to do that work again. We can just show them that we remember that we did that in part A. And if we refer them back there, then we get whatever points are attached to that value in part C. So this is y minus y1. And now we need the slope at x equal 3. We've already clearly shown them here that we recognize g prime as f, so we can just show them we're after f of 3. We come up here to our graph and we see at x equal 3, y equals -1. So this is negative. We usually don't write times -1, but there's our answer right there. So a lot of things to consider. It's not really that difficult, algebra or calculus. There's not a lot of it difficult. The challenging part of it comes in trying to figure out what you have to show them in order to get all the points. Because I think most students do really understand the relationships. So part D, find the x coordinate for each point of inflection of the graph of g on the open interval from -2 to 5 and justify your answer. Well, we've already shown them in part B that we understand g prime equals f, and we could show them therefore we understand g double prime equals f prime. And so we clearly need to tell them, based on our information on f prime, when g will have a point of inflection. So g of x will have a point of inflection when f of x has an extreme value. We did an example before on the last set of videos where we used the slope for a justification. Here I'm going to use monotonicity of f because that is where f prime would be positive. G will have a point of inflection when f has an extreme value. This occurs at x equals. So we're looking for maxes and mins anytime that monotonicity changes on f. Now, we have a little, bump here, but f goes from decreasing and stays decreasing. So even though the second derivative would not be defined here, and that would be a potential inflection point, it's not an actual inflection point because f does not change monotonicity. So this is the biggest kind of curveball, because f itself does go from positive to negative outputs, but when we're talking about point of inflection, we're looking at slopes or monotonicity on f. So this only occurs at x equals 0 and at x equals 3. And I cannot stress this enough. You absolutely, beyond a shadow of a doubt, will see functions defined as integrals all over the BC exam in May. You'll see it all over the multiple choice, and you're highly likely to have it as a free response question. So work the problems when you come to class and we do homework. Work the problems diligently and make sure you understand these relationships and pay attention to all the little subtleties on how you're going to have to show your work. Let's do another example in a different context. F is the differentiable function whose graph is shown in the figure. The position at time t, so now they've put us into position, velocity, acceleration instead of f, f prime, f double prime kind of thing. The position at time t in seconds of a particle moving along a coordinate axis is this function defined as an integral. Here we aren't shown that it is s of t, but we can clearly see from the notation that it is s of t, and since we can't use t for our dummy variable, they've chosen to use x, but they could have used any dummy variable here at all. Don't let notation trip you up. All right, so part A says, what is the particle's velocity at t equal 3? Well, we know that velocity is the derivative of position. And we want to show the AP reader that we recognize that. And we recognize, therefore, since position is a function defined as an integral, we're going to take the derivative with respect to the independent variable from 0 up to t of f of x dx. And that is going to be f of t. All right? So the velocity at 3 is going to be the output of this function at 3. And we can clearly see that the output of the function at 3 is 0. So you should begin to see us doing the same type of work over and over and over again. But the main thing that I want to make sure that you know is a vast amount of points, especially on free response, are going to come from justifying how you got here, proving to the AP reader that you know what the relationships are in Fundamental Theorem of Calculus Part 2. All right, same function, same definition. Here's Part B. Is the acceleration of the particle at t equal 3 positive or negative? We've already defined that we know velocity is the first derivative of position, and that we said that the velocity was this function f of t. We need to show that we know that acceleration now is the first derivative of velocity, so we're looking at the slopes on this function f. So we're actually after, for the acceleration at 3, we're after the slope on this function f at 3, and we're really only interested in whether it is positive or whether it is negative. And we can clearly see the slope at 3 here is a positive value. So the acceleration of the particle at time t equal 3 is positive. And there's our justification for why we know that's true. So here's part C. What is the particle's position at t equal 3? So it's asking for s of 3. Well, we know s of t is this function, so s of 3 has to be the accumulated area from 0 up to 3 underneath the function f of x dx. So we're going to go to the graph and we're going to use our knowledge of geometry, that's a triangle, to find that accumulated area. So it's 1/2 the base, and we can see here that the base of this triangle is 3, times the height. The height of this triangle is -6. All right, so this is -9. So the particle's position at t equal 3 is -9. And I have to show this step in order to get credit for that answer. Otherwise, it's a bald answer. Part D, when does the particle pass through the origin? The particle will pass through the origin when s equals 0. All right? The particle will pass through the origin when s of t equals 0. We're not looking at the graph of s. We're looking at the graph of f, or s prime. And so we're going to need to prove that we're looking for a t value where the accumulation under this function equals 0.